another circuit is shown in the pictures. We have a resistor, right, with the resistance equal to the 47 ohms connected in the series with an inductor, so let's say the L2. So now this branch connects in parallel with another capacitors, and then this group connected in the series with another inductor and then to the AC source here. So let's say that the potential difference across this resistor equal to the V out. Okay, so let's make this one to be the amplitude of the potential difference. And we know that the current through the AC source, and then for the L1, right, we have the amplitude equal to the 10 ampere and the angular frequency equal to the 120 pi radian per second. So now for the part A, we just want to compute the ratio of the V out over the V in, where the V in is the maximum voltage the power supply delivers to the circuit. On the other hand, the V in here is going to be the potential difference across the AC source here. And then for the part B, compute the power dissipated in the circuit. Okay, so let's just start from the part A first. Okay, so now to get the V out, right, to get the V out over the V in, it means that we are trying to link the V out to this branch first, and then this branch will be combined with another branch to be the whole thing here, and then we're gonna combine the whole thing here to the L1, and then finally we can link the V out to the V in here. Okay, so that's gonna be the idea how we can work on this one. So let's consider this branch. Okay, so let's say that this can be the branch maybe 2, okay, because we have the 2 here. So let's say that this will be the branch 2. So what we know about the branch 2, so let's assume that the current through the branch 2 equal to the I2, and then the potential difference across the branch 2 here equal to the delta V12, okay, because it's going to be the same as the potential difference across this thing, because I mean this branch and this branch are connected in the parallel to each other, so that's why the potential difference must be the same. And then the phase of this branch must be the phi2. Okay, so let's define this way. So now for the first branch, let's say that the current equal to the I1 and the potential difference across this branch equal to delta V12, so it just be the same as this. Okay, and the phase equal to the phi1. So let's define these variables by ourselves here. Okay, the second branch. Okay, let's consider the second branch. Okay, let me just write down the phasor diagram first, okay, because it's going to be helpful later. So we know that the L2 and the R connected in the series, so it means that the I2 must be the common variables. Then let me just make the I2 to be the horizontal axis here, the I2. Okay, so this is the amplitude of the I2, and then the potential difference across the R, right, must be in is in the same phase as the I2, so we can get this arrow. Okay, so let's say that this is going to be delta V. Wait. Because the questions in the questions they use V, not delta V, right? So, okay, so they use V, not delta V. So in this case, again, let me just take the delta out. Okay, let me just take the delta out to make it simple. But you need to keep in mind that this V just the same as the delta V here. Okay, so let me just take delta out as well. So this is going to be the delta V across the resistor R. okay, delta V across the resistor R, which is equal to the V out, right, which is equal to the V out. Okay, so now this one, we know that the potential difference across the L2, we have the phase leading the current by 90 degree. Okay, remember from the table, the potential difference across the L2, we have the phase leading the current by 90 degree. So in this case, the V of the L2, we just point to this direction. So now let's combine these two vectors together. Okay, so let's combine these two vectors together. Okay, so we have this one, right? So this one is going to be the V12, the potential difference across the whole thing here. And now this phase angle, right, is going to be equal to the phi 2. Okay, the one that we just defined here, the phi 2. Okay, so let's find the number, right? So let's find the number. Let's just start from, okay, we know the omega and we know the L2. We can find the XL2. We can find the XL2 equal to the omega and then times the L2, right? The omega is just equal to the 120 pi. So this is the omega. And the L2 is 0.1x0. Then the XL2 is just equal to the 67.9 ohm. Okay, good. Then next step is to find the C2, the impedance of the second branch here, equal to the square root of the R square and then plus the XL minus the XC and then square. But then again, right, this is the L2. Then again, so the XC equal to the 0 in this branch. So here we have that equal to the square root of the R. R is what? R is the 24.0 ohms. And then plus the XL2. The XL2 is 67.9 ohms. Sorry, 67.9 ohms and square, and then totally square root, right? So then we can get the C2 equal to the 82.5 ohms. Okay. So now when we get the C2, we can find the let's find the phi2 first. Let's find the phase first. So now this phi2, right, is going to be equal to the arctan of the opposite and then over the adjacent. The opposite is the VL2 and the adjacent is the VR, right? VR, which is equal to the arctan of the XL2 and then over the R. Okay, equal to the arctan of the, okay, the XL2 equal to what? XL2 equal to the 67.9. And then the R is just equal to 34.0 ohms. Then we get the phi2 equal to the 55.3 degree. So that's going to be the phi2. Okay. So now finally we just want to link between the V12 and the I2 together. So we know this relationship. No, not that space. Let me go to this one. Okay, we know that the V12, okay, the V12 equal to the I2 and then times the C2, right? So it's going to be equal to okay, the 82.5 and then times the I2. Okay, so now you see that we don't know the I2 yet, so just leave the I2 as this one. Okay, but when we work on this one, work on this one, and work on this together, work on this together, then we can find the I2. Okay, so that's going to be the idea how we can solve for this. Good. Okay, so next, let's consider the first branch and the second branch together. Okay, so let's combine these two branches together. It means this one and this one, let's combine together. Okay, so now let's look here. The first branch and the second branch are connected in the parallel. It means that the potential difference must be the same, right? So now I'm gonna make the V12 to be the common variables, I mean, for these two branches here. So the V12 in the phasor diagram is gonna be the horizontal axis here. Okay, next, okay, so let me just write down the I2 for the second branch first. So now from this phasor diagram, right, you can see that the phase of the I2 is lagging the phase of the V12 by V2. Okay, so it's gonna go like this one. Yep. Okay, so this is gonna be the I2. Okay, the I2, and let's say that this angles equal to the V2, right? Equal to the V2 here. Good. So now for the first branch, we know that the current through this capacitor, right? The phase of the current through this capacitor will lead the phase of the potential difference by 90 degrees. Okay, from the table, the phase of the current I1 through this capacitor will lead the phase of the potential difference across the capacitor by 90 degrees. Then in this case, we can get that this is going to be the I1, right? The I1. Okay, and this will be the 90 degree as well, and that's it. Okay, so then here again, right, we can get that the I for the horizontal is going to be equal to, so we need to break this I2 into this component and to this component. Okay, so let me just write down. We can get this one, right? It's going to be equal to the I2 and then times the cosine phi2, and then here it's going to be the I2 times the sine phi2. So then we have that the IH, so the current in the horizontal component, is going to be equal to the I2 and then times the cosine phi2. Okay, and then for the I vertical components, it's going to be equal to the I1, so this one, and then minus the I2 sine phi2, so just subtract with this one. Okay, so that means that the phasor diagram, right, is going to be changed to this picture. So this is going to be the IH, and then this is going to be the IV. Okay, then again, right, so we need to combine these two components by using the Pythagorean theorem. Then we can get this vector. Okay, so we can get this vector, but then what is this vector? Okay, what is this vector? So now you see, if we combine this and this together, then we will get this group, right? Okay, it means that the current through this circuit or this group is going to be equal to the I naught here. Okay, it's going to be equal to the maximum current, the I naught here. Why? Because this the source here, right, connected in the series with the L1 and connected in the series with the whole thing here as well. So it means that the current passing through the whole thing here must be equal to the I naught as well. Okay, so now we get this one to be the I naught equal to the 10.0 ampere. Okay, but then this phase we don't know yet, so let's say that it's just equal to the phi12. Okay, equal to the phi12 here. Okay, so let me just wrap up everything again. The whole thing here, right? So okay, for the whole thing here, right? So let's say that the current equal to the I, so equal to this current, and potential difference equal to the V12, right? The same as this one and this one, and then the phase between the current and the V12 is just equal to the phi12. Okay, good. Okay, so now we can get that the I naught, right, the I naught square, okay, so this guy square is going to be equal to the IH square and then plus the IV square, then it just equal to, okay, so the IH equal to what? Equal to this, equal to the I2 times the cosine the phi2 and then square, right? And then plus the IV is just the I1 minus the I2 times the sine of the phi2 and then square. Okay, so now the question is, can we simplify this thing? The answer is yes. Okay, we know that V12 equal to 82.5 times the I2, right? It means that we can find the I2 in terms of the V12 as well. Okay, so we can just plug in the I2 here into this and into this. Okay, and the phi2 we also know it already. But then how about the I1? The I1 is going to be the current passing through this capacitor, right? So we can find the I1 in the terms of the V12 as well. Okay, we can find the I1 in the terms of the V12 as well. Let me just write it down here. Right? So let's say that the XC, okay, equal to the 1 and then over the omega times C. No, wait, I think it's the bad idea because we don't have any space left. Okay, so let me just write down here. The XC equal to the 1 over the omega C. 1, okay, 1 over omega is this one, 120 pi, right? This is the omega, 120 pi, and then times the C. The C is equal to 105 microfarad. Okay, and 1 over this, right, equal to 25.3 ohms. That's be the XC. So then we can get that the V12, right? Okay, so let's consider the first branch here. The V12 is going to be equal to the I2 times the XC, okay, equal to 25.3 times the I2. So that's going to be the relationship between the I2 and the V12 here. Okay, so then let's just plug in the I2 and the no, wait, sorry, this must be the I1. This must be the I1. Okay, it must be the I1, because the I1 is to be the current through this capacitor. Okay, so let's just plug in the I1. Oh, I need to change this as well. Let's plug in the I1 and the I2 into this equation. Okay, so we have the I2 equal to this one, right? It's equal to the V12, and then over 82.5, okay, times the cosine phi 2. Phi 2 is equal to the 55.3 degree. Okay, and then square plus the I1. The I1 is here. It's just equal to the V12, and then over the 25.3 minus the I2. I2 is the V12, and then over the 82.5, and then times the sine of the phi 2, right? Phi 2 is just 55.3 again, 55.3 degree, and then square. Okay, and now on the left hand side, right, the I0 equal to what? Equal to the 10 ampere. Okay, this is the I0. So we have the 10.0 and then square. Okay, so now you see from this question we can solve what? We can solve the V12, right? We can just solve for the V12. Okay, so let's just simplify it. So here we have, okay, let me just bring the V12 out of this equation. So we have the V12 square, okay, and then we have the cosine 55.3 degree, and then over the 82.5 and then square, okay, plus 1 over the 25.3 minus the sine of the 55.3 degree, and then over the 82.5 and then square, okay, and the cross the square bracket here, right? And then that's quite simple. You can just solve for the V12, right? Then finally we can get that the V12 here is going to be equal to the 329 volts. Okay, the 329 volts. So it means that this value is going to be the amplitude, okay, of the voltage across this whole thing here, okay, the 329 volt. And the current we know already equal to the 10 ampere, right? Just the same as this one. So the next step is to find the V12, okay, to find the V12. So how can we find the V12? We can just find the V12 from this phasor diagram, right? Okay, so let's continue. The V12 equal to the arctan of what? Okay, the opposite over the adjacent, right? So it's be the IV over the IH here. Then again, let's just plug in the IV and the IH, right? This one into that equation. Okay, let me just copy first. Okay, equal to the IV is the I1 minus the I2 times the sine of the phi2, and the IH, right, just the I2 times the cosine of the phi2. Okay, the next step is just to plug in the I1 and the I2, right? Okay, so now we know can we find the I1 and the I2? Yep, right? Okay, so let's find the I1 and the I2 first. Okay, then we get that the I1, okay, from this equation, right? The I1 equal to the V12, the 2329, and then over the 25.3. Okay. 329 over 25.3 equal to the 13.0 ampere. Okay, this will be the I1. So now for the I2, okay, for the I2 we can use this equation equal to the V12 over the 82.5. The V12 82.5 I got the 3.99 ampere. Okay, that's great. So now we know the I1 and the I2 already, so that's really simple, right? It's gonna be easy. Okay, equal to, again, the arctan of, okay, the I1, right, minus the I2 times the sine of the phi2, and then over the I2 times the cosine of the phi2. Okay, so then you get the answers to be equal to 76.9 degree. So that's be the phi12. Okay, and that's it. Okay, so now the final step, right, it just combine this, the whole thing here with the L1. Okay, so just combine the whole thing here with the L1. So now you can see that this whole thing and the L1 are connected in the series, so it means that the current must be the same, right? The current must be the same. Then we have that, okay, so consider the whole circuit. Okay, the current must be the same, so if we just make the current to be the horizontal axis here, so it just equal to the I0, right, the 10.0 ampere. That's be the current. So now for this group, right, okay, this group, it is this one, this phasor diagram. So you can see that the V12 is lagging the current by the phi12. Okay, this V12 is lagging the current by the phi12. So in this case, okay, so the V12 will point to this direction. Okay, this will be the V12, and this angle is going to be equal to the phi12 as well. So now for the inductor, right, we know that the potential difference across this inductor will have the phase leading the current by 90 degree from the table again. Okay, the V of the L1, right, we have the phase leading the current by the 90 degree, so we can get that this going to be the VL1. Okay, and just make it the 90 degree to the current here. So then again, right, so we can just break this vector into the two components. So we have the V12 and the cosine the phi12, and there's going to be the v12, and then times the sine of the v12. Okay, so then later our phasor diagram can be converted to something like this will be the I naught, right? To here it's going to be the VH, okay, and to this one it's going to be the V of the vertical, okay, and then again we can just combine these two as the vectors. Then we can get this vector, right? Okay, we can get this vector. So then what is this vector? This vector is going to be the V in, right? The V in of the AC source here, okay? Because when we combine this and this together, we will get the potential difference across the whole thing here, right? So it must be the same as the potential difference across the AC source, which is equal to the V in, okay, the V in. And let's say that the phase between the V of the AC source and the phase of the current, right, is going to be equal to the phi, okay, equal to phi. So now we need to find the V in and the phi. Okay, so we just want to find the V in and the phi. Okay, so let's just start from finding the VH and the VV first, and then to find the V in, right? But then before finding the VH and the VV, we need to know the VL1 first. Okay, how about just start from the VL1? The VL1 is going to be equal to the current through the inductor, right, which is equal to the 0, and then times the inductance, the reactance of the inductor, so the XL1, okay, equal to the I0 equal to the 10.0 ampere, the XL1 equal to the omega times the L, the omega just 120 times the pi, right, and then times the L1 is 0.120 Henry. Then we can get the VL1 to be the 452 volts. Okay, this will be the VL1, the voltage amplitude across this inductor here, the 452 volts. So now for the VH, right, the VH, okay, so we have only this component. It's going to be equal to the V12 times the cosine phi 12 equal to the V12 equal to the 329 volts, and then times the cosine of the phi 12. Phi 12 is this value, it's just the 26.9 degree, right? Then it's going to be equal to 74.6 volts. So that's going to be the VH. So now how about the VV? The VV is going to be this component. Okay, so it's equal to the VL1 and then minus the V12 times the sine of the phi12 equal to VL1 just the 452 minus the V12, which is the 329, and then times the sine of the 26.9 degree. Okay, so we can get that the VV is going to be equal to the 132 volts. That's great. So now we have this horizontal component and the vertical component already. We can find the V in. Okay, the V in here, the V in here is going to be equal to, okay, from Pythagorean theorem, the square root of the VH square, right? And then plus the VV square equal to the square root of, okay, the VH is 24.6 square plus the VV is the 132 square and then square root. So then finally we can get that the V in is just equal to the 152 volts. Okay, this is what we get. And also we can find the phase difference between the V in and the I naught, right? So we can use the phi equal to the arctan of, okay, the opposite and then over the adjacent. So it's just the VV and then over the VH, right, equal to the arctan of 132 over the VH is 24.6. So then we can get that the phi angle here equal to the 60.6 degree, and that's it. Okay, so this is what all we need. Okay, by the way, let me just write down the potential difference across the source here. Okay, let me just write down. So let's say that this V, okay, this V. VT equal to, okay, this thing, the 152 volt, and then times the sine of the omega t, right, because the phase of the current is just equal to omega t. But now what is the phase of the V? So then from this phasor diagram, right, you can see that the phase of the V is leading the phase of the current by phi. Okay, so then it must be plus the 60.6 degree, and that's it. Okay, so this will be the function of the potential difference across the source here. But now what is the question? We just want to find the ratio, right? We just want to find the ratio of the V out and then over the V in. Okay, so let's do this. We can get that no space. Okay, that's fine. The V out and then over the V in, right, is gonna be equal to, what is the V out? We don't know the V out, right? We don't know the V out. Okay, we don't know the V out, but we know that the current through this one equal to the I2, and we know the resistance, so then we can find the V out here. Okay, then okay, should start new. Okay, the V out, right, the V out equal to the current through the resistor, which is equal to the I2, and then time is resistance, the R. Okay, because the current through the resistor equal to the I2 here, then times the resistance. So the I2 equal to what? The I2 equal to the 3.99 ampere, right? And then times the R. What is the R? The R is 47.0 ohms. So we can get that the V out is just equal to the 187 volts. Okay, so then finally we have that the V out and then over the V in is going to be equal to the 187, and then over the V in is the 152. Okay, which is just the 1.23. So that's going to be the answer. Okay, so maybe you just curious that why the V out is greater than the V in, right? So you don't need to mind this one, because don't forget that what we are writing right now is the amplitude of the potential difference across the source and then across the R, right? So it's possible that the V out can be greater than the V in. Okay, but then if we take into account the phase of between the current and the voltage, right? So ensure that this the real V across this one will be less than the V across the source here. Okay, so no big deal. Now, okay, so part B, right? Part B. Okay, so compute the power dissipated in the circuit. So it's just quite similar to what we have done many times ago, right? So we have only this resistor in the circuit. It means that if we just want to find the power dissipated in the circuit, we just find the power lost via the resistor, and that's it. Okay, or maybe you can just look for the whole circuit, you will get the same answer. Okay, so now let me just look for the whole circuit. Okay, let me just look for the whole circuit. So then this P, right, equal to, okay, the 1/2 and then times the I naught, the V naught, and then times the cosine phi. Okay, the I naught here is going to be the current amplitude of the whole circuit. The V naught is going to be the voltage amplitude of the whole circuit, and the phi is going to be the phase angle between the I naught and the V naught here. Okay, so let's just put in the number. The I naught is just the 10.0, right? And the V naught, the V naught, we just call it as the V in, sorry. It's just the V in, okay? The V in is 152, and then times the cosine phi, 60.6 degree. Okay, so the answer is going to be equal to the 373 watt. Okay, so that's going to be the answers. Okay, so then how about if we just look only the resistance? Okay, if we just only for the resistance, so we expect that the answer must be the same, right? Okay, so let's see. We have the power equal to P equal to the 1/2. Okay, so then it's going to be the current through the resistance. So we use the symbol to be the I2, right? And the potential difference across the resistor is with the V out. Okay, so we have the I2 here, and then it's going to be the V out, right? And then cosine 0 degree. Okay, so don't forget that the phase difference between the current through the resistor and the potential difference across the resistor equal to the 0 degree. Equal to the I2. What is the I2? The I2 is this value, 3.99 ampere. The V out, right? The V out is 187 here, and cosine 0 equal to 1. Okay, so again you will get the same answer to be the 373 watts. Okay, so it's be the same answer. Okay, then how about if we just consider the second branch? Okay, so for the second branch, so it means that if we look for this branch, right, the second branch, so now you can see that the second branch we have only one resistor. It means that the power loss via this branch must be the same as power loss via this resistor only. Okay, it should be the same. Okay, so we have P, right, equal to the 1/2, and then times the current through this second branch equal to the I2, and then times the potential difference across the second branch equal to what? Equal to the V12, right? And the phase equal to the phi2 here. Okay, so let's see. Times the V12 and then times the cosine of the phi2. Okay, so let's just put in a number. The I2 is just the 3.99 ampere. So then how about the V12? Okay, so let's check. V12 is the 329 volts. Okay, the 329 volts. And then the phase, right? The phase here equal to 55.3 degree. Okay, and that's it, right? So you will get the same answer as the 373 watt as well. Okay, okay, one more thing. You can find the power loss via this group of the branches. Okay, you can find the power loss via this group of the branches as well. So now you need to use the I for the whole circuit here. You need to use the V12 and the phase difference between this I and this V, right? Okay, so let's see. So we can get that the P here, right, equal to the 1/2, and then for the I of the whole circuit, it's going to be the I naught, right? Because I mean the current here will passing this whole group, so the current must be the same. Okay, so the I naught, and the V is just the V12, and then times the cosine of the V12. Okay, because the phase difference between these two just equal to the phi12 here as well. Okay, then let's just plug in the number. Equal to the 1/2, the I naught is just equal to the 10.0 ampere, right? The V12 equal to the 329, and then times the cosine of the phi12. The phi12 is equal to what? 36.9 degree here. Okay, equal to the 373 watt as well. So now you see, if you do everything correctly, so you should get the same answer. Okay, so it means that maybe you can just use this, to check your results as well. Okay.